Right now, somewhere in our galaxy, there is a region of space where the rules of physics break. Light cannot escape it. Time slows to a crawl near its edge, and no signal, no matter, no information has ever returned from inside one. We call it a black hole, but most people get this wrong. There is not one type of black hole. There are at least 10. Some are smaller than an atom. One single example is wider than our entire solar system, and a few of them are drifting between the stars completely hidden in plain sight. In the next 14 minutes, we cover every single one. Number 1, the stellar mass black hole. This is the kind of black hole you have probably pictured in your head. It is what is left behind when a massive star, at least 20 times the mass of our sun, runs out of fuel and collapses under its own weight. A stellar mass black hole typically contains between 5 and 100 times the mass of the sun, compressed into a region only a few miles across. Picture the entire mass of 20 suns crushed into something the size of a small city. The density is so extreme that gravity at the surface becomes effectively infinite. Nothing can escape, not even light moving at 670 million miles per hour. The first black hole ever confirmed was a stellar mass one called Cygnus X1, identified in 1971. It is about 21 solar masses, and it orbits a blue supergiant star, slowly eating the star's outer atmosphere. Astronomers estimate there are around 100 million stellar mass black holes in our galaxy alone. Most are completely invisible. We only spot them when they are pulling material off a companion star or when their gravity bends the light from a star behind them. The nearest known one is called Gaia BH1. It is roughly 1,560 light-years from Earth, close enough in cosmic terms to be uncomfortable. Number 2, the intermediate mass black hole. This one is one of the strangest puzzles in modern astronomy because for a long time, scientists were not sure they actually existed. An intermediate mass black hole, or IMBH, sits in the gap between stellar mass and supermassive black holes. It weighs anywhere from 100 to 100,000 times the mass of the sun. That sounds like a wide range, but here is the problem. We cannot get one to form easily. A stellar mass black hole forms when a single star collapses. A supermassive black hole, the kind we will get to next, forms over billions of years through some process we still do not fully understand. But the middle ground? Nothing in physics naturally produces a black hole of, say, 10,000 solar masses in a single event. For decades, astronomers debated whether intermediate mass black holes existed at all. Then, starting around 2009, observations of a few objects, including one called LX1 in the galaxy ESO 243-49, gave us strong evidence that they are out there. They appear to sit in dense star clusters, possibly forming from runaway collisions of smaller black holes. The most likely answer is also the most unsettling. Intermediate mass black holes are the missing link in how the universe builds its largest gravitational monsters. Number 3. The supermassive black hole. Now we leave the realm of stellar physics entirely. A supermassive black hole contains millions to billions of times the mass of our sun. Compress that down to a single object, and you have something with an event horizon larger than the orbit of Mercury, sometimes larger than the entire inner solar system. At the center of nearly every large galaxy in the universe sits a supermassive black hole, including ours. The one at the heart of the Milky Way is called Sagittarius A star. It weighs around 4.3 million solar masses. It is about 26,000 light-years away from you right now, and it is the gravitational anchor that the entire galaxy quietly rotates around. In April 2019, astronomers released the first ever direct image of a supermassive black hole, Messier 87 star, at the center of the M87 galaxy. That object contains 6.5 billion solar masses. Its event horizon is so large that light takes more than a day to cross it. But here is the part that still has not been explained. We have found supermassive black holes that existed when the universe was less than 1 billion years old. They should not have had time to grow that large. Something we do not yet understand allowed them to form fast. But those 3 are just the beginning. The next ones get significantly stranger. Number 4, the ultramassive black hole. The largest black holes ever measured are not just supermassive. They are in a class so extreme that astronomers gave them their own label, ultramassive. To qualify, a black hole has to contain at least 10 billion times the mass of the Sun. The current record holder is an object called TON 618. It sits roughly 18 billion light-years away, which means the light we see from it left when the universe was less than a quarter of its current age. TON 618 is estimated at 40 billion solar masses. Try to picture the scale. Its event horizon is approximately 1,300 astronomical units across. 1 astronomical unit is the distance from the Earth to the Sun. That means the event horizon of this single black hole is more than 40 times the diameter of our entire solar system out to Pluto. You could fit the orbit of every planet, every dwarf planet, and the entire Kuiper belt inside it, and still have room left over. A newer candidate, called Phoenix A*, may be even larger, possibly 100 billion solar masses, though that figure is still being verified. These objects are not just black holes. They are the gravitational engines around which entire galaxy clusters arrange themselves. They distort space-time so violently that near them, the geometry of the universe itself rewrites. Number 5. The rotating black hole, also called a Kerr black hole. Here is a fact most people do not know. Almost every real black hole in the universe is often spinning extremely fast. When a massive star collapses to form a black hole, the angular momentum of the original star does not disappear. It gets concentrated. The black hole inherits the spin. And because all the original mass is now compressed into a tiny region, the rotation becomes almost unimaginably fast. The supermassive black hole at the center of the galaxy, NGC 1365, is spinning at approximately 84% of the speed of light at its event horizon. Another, called GRS 1915, has been measured spinning at over 98%. We are talking about objects with the mass of millions of suns rotating that fast. Rotation changes everything about how a black hole behaves. A spinning black hole drags space itself around with it, a phenomenon called frame dragging. Around the event horizon, there is a region called the ergosphere, where space is being twisted so violently that no object inside it can stand still. You would have to move faster than light just to remain in one place. In theory, you could even extract energy from a rotating black hole by throwing matter into its ergosphere, a process named after the physicist Roger Penrose. A sufficiently advanced civilization could, in principle, use a spinning black hole as a power source. Number 6. The binary black hole system. Sometimes two black holes orbit each other, and eventually they merge. A binary black hole forms when two massive stars in a tight orbit both die and collapse. The resulting black holes continue to orbit each other, spiraling closer over millions or billions of years. As they spiral, they radiate energy away in the form of gravitational waves, actual ripples in space-time. On September 14, 2015, the LIGO Observatory detected the first ever gravitational wave signal. It came from two black holes, 36 and 29 solar masses, colliding 1.3 billion light-years away. The merger happened in less than a fifth of a second. In that fraction of a moment, 3 solar masses worth of energy were converted directly into gravitational waves. 3 solar masses vanishing, becoming pure space-time distortion. For that instant, that single event released more power than every star in the observable universe combined. Since then, LIGO and its partner observatories have detected dozens of binary black hole mergers. Some involve black holes too large to have formed from any individual star, which means the universe is producing intermediate mass black holes through these collisions, possibly explaining the IMBH mystery from earlier. A binary black hole is one of the most violent objects in physics. And right now, somewhere in our galaxy, there are pairs slowly winding toward each other. The next merger event has already begun. We just have not heard it yet. Everything we have covered so far has been observed. The next ones, most have not. Number 7. The charged black hole. In theory, a black hole can carry 3 properties: mass, spin, and electric charge. We have already covered mass and spin. The third, electric charge, gives us a strange theoretical object called a Reissner-Nordstrom black hole. A charged black hole would have 2 event horizons instead of 1. The outer one behaves like the event horizon you would expect. The inner one called a Cauchy horizon, is far weirder. According to general relativity, inside it, the predictable rules of cause and effect begin to break down. Different timelines could converge on the same point, but here is the catch. Charged black holes almost certainly do not exist in nature. Our universe is full of free-floating plasma, positive and negative particles drifting through space. Any black hole that developed an electric charge would attract the opposite charge from its surroundings and rapidly neutralize itself. So the charged black hole is, for now, a mathematical possibility, a solution to Einstein's equations that the universe seems to forbid in practice. Number 8, the rogue or wandering black hole. Not every black hole is anchored to a galactic center or paired with a companion star. Some of them are drifting through interstellar space alone, with nothing visibly orbiting them. No accretion disk, no doomed companion, completely dark, completely silent. These are called rogue black hole. We cannot see them directly. They give off no light. They make no radio signal. They are detectable only when their gravity bends the light of a star behind them, an effect called gravitational microlensing. In 2022, astronomers confirmed the first definitive isolated rogue black hole. It is about 7 solar masses. It sits 5,000 light-years away, and it was identified only because it briefly distorted the light of a distant background star. Based on stellar death rates over the age of our galaxy, astronomers estimate that there are around 100 million rogue black holes drifting through the Milky Way. Most of them will never be detected. There is no reason one could not be passing through the outer solar system at this very moment. You would never know. Number 9, the primordial black hole. This is where things get genuinely strange. A primordial black hole is one that did not form from a dying star. It formed in the first fraction of a second after the Big Bang, when the universe was still a hot, dense soup of energy. In some places, the density was so extreme that regions of space collapsed directly into black holes without ever passing through a stellar phase. If primordial black holes exist, they could come in a vast range of sizes. Some would weigh as much as a mountain compressed to the size of an atom. Others might weigh thousands of solar masses. The smallest ones would have already evaporated by now via a slow energy leak called Hawking radiation. But the ones larger than about 100 billion tons would still be out there. Some physicists believe primordial black holes could account for part, or even all, of the dark matter that makes up 27% of the universe. We have never directly detected one, but if they exist, they have been silently shaping the structure of the cosmos since the universe's first second. And the last one on this list is something most people have never heard of. Number 10, the micro black hole. At the smallest scale physics permits, there is theoretically an object so tiny it sits at the border between general relativity and quantum mechanics. A black hole no larger than a subatomic particle. A micro black hole would have a mass of around 22 micrograms, packed into a region smaller than a proton. Imagine the mass of a small dust mote, compressed into something 1 trillion times smaller than an atom. These objects are predicted by certain theories of quantum gravity. Some physicists once speculated that the Large Hadron Collider at CERN might create them in particle collisions. None have ever been observed. If one did form, it would evaporate via Hawking radiation in less than a billionth of a second, releasing all its mass as a flash of high-energy radiation. The micro black hole is the smallest object physics permits, the boundary between mass and pure energy, the point where the universe stops being predictable. And some physicists suspect that at the quantum scale, micro black holes are continuously forming and evaporating throughout empty space, making the vacuum itself behave like a restless, unstable foam. 10 types of black hole, from stellar collapse to primordial fragments to quantum-scale ghosts at the edge of what physics permits. What ties them all together is the same single rule. Mass, when concentrated past a certain point, breaks the universe. Light cannot escape it. Time slows around it. Information vanishes inside it. And we are still, 50 years after the term was coined, only beginning to understand what is actually inside. Next week, we cover every way a star can die, the violent and beautiful processes that create most of the black holes you just learned about. Subscribe so you do not miss it. And as always, the universe explained simply.